Now we're going to try to find the torque required for this kind of centrifugal pump. So the water or fluid comes in down this pipe and enters the pump, and it's goes up and down into the regions where the blades are. So the blades are spinning. So this is a side view. You're just seeing the faces of the blades as they would spin in and out of the paper here. And then if you look from the front, you'd see this shaded section would be where the blades are. So the liquid is going to come into the middle, flow out to the outer into the blades, and then it's going to be pushed, outward from the blade. So the fluid's going to leave from the outside edge of this blade region, enter the inside edge. So if we want to do a control volume analysis of this to figure out how much torque is required to drive this pump, so that's what we're going to look for. So we're trying to find the torque. Find torque to drive the pump. And so we're going to do that by doing a control volume analysis of the shaded area. So I'm going to do that based on the moments. So the sum of the moments in the shaded area is equal to the time derivative of the change in R cross V, that is the angular momentum we're trying to calculate here, right? Times the mass, the density, we're stepping in for mass there, times the volume, integrated over that volume of that control volume, plus the change in angular momentum of the fluid that leaves the system or enters the system. So R cross V again, but now we have the density, and then we have the dot product, of course, of the velocity with the surface, because that's the fluid either entering or leaving our shaded volume. So right away we can say, look, our pump's going to operate at a steady state sort of situation here. So we're not going to have any time dependence. So this term is going to go to 0 because it's steady state. So we can drop this term, as we so often have done with control volume analysis. Almost every control volume analysis we've done in this class, I believe, we have had steady state operation. So we're really just going to be focused on the change in momentum of the fluid, angular momentum of the fluid leaving and entering our control volume. So doing that, we're going to simplify the equation, obviously, down to just that term. So we have the sum of the moments has to be equal to this change that happens to the fluid as it enters and leaves. So we have rho v dot n hat dA, and then we kind of recognize this. So what is this? This is actually m dot entering and leaving, right? That's going to be your density, your velocity dotted with the surface normal that's going to cause it to either enter or leave, depending on which surface you're at. So we're going to recognize this is going to come out to be m dot. So we're going to go ahead and say that we know that already. And so that's going to be minus r cross v at the inlet times m dot in plus r cross v at the outlet with m dot out there. So the reason for this minus sign is because we know that V in is going to be opposite the surface normal at the inlet. That's what in means, right? It means the velocity is coming in, and the surface normal is going to be pointed out. That's the definition of the surface normal. So we believe that that's going to give us that negative sign. So this is negative at the inlet, positive at the outlet. That's the sum of the moments. So then we can say, all right, we can recognize, first of all, that m dot in has to equal m dot out in order for mass conservation to exist. We can't have mass accumulating inside the pump indefinitely at steady state. That's just ridiculous. Turn our pump into a black hole or something, or have a vacuum. Just silly. So we're not going to have that. So we're just going to have one m dot. And of course, we know that it's, at the inlet, it's r1. So we're going to use the r1 vector for that. And the inlet velocity, and of course we have this is all minus because we're still at the inlet, and then we have the R2, which is the outlet velocity outlet radius crossed with the outlet velocity, and m dot there as well. Okay, so that's going to be our formula. We know these values, at least we can write them down in a way that makes sense. So the inlet vector, we're going to have two components. The radial component we're going to call it v sub n, which is the velocity normal to the surface. And then the theta component is going to be v sub t, and there is no z component. So we're just not doing z. There's nothing happening in that direction. So I'll draw a picture so you can see it more clearly. We're going to have v sub n coming normal and v sub t going tangential to the surface. So this is that's our breakdown of Vn. And then we have, and that's all at the inlet, of course. And then we have R1 here. And we know R1 has only a radial component. It only points in the radial direction. So the R vector, R1 vector is just R1, 0, 0. And the R2 vector, similarly, is just equal to R2, 0, 0. So that's that. So we have all of our vectors there. So we're going to use that in the next bit of lecture to go ahead and try these do these cross products. You can go ahead and try to do these cross products. You have all the vectors you need. The V out vector, of course, is going to look a lot like the V in vector. It's going to say out right here. So that's going to be our cross product. So the next bit will actually do that.